Hi and welcome to Lecture 5 on Sequential Circuit Design. In this lecture we're going to go over the design procedure. This is going to be fairly detailed, and then we're going to use that design procedure to do a sequence recognizer example in part 2. In part 3 we're going to look at state assignment using examples of counting order and gray code, and then part 4 we're going to do another state assignment which is called one hot assignment, and finally in part 5 we're going to look more at flip-flops and introduce a few new flip-flops which we can use. So let's get into the design procedure. So the design procedure is basically the same as what we had for the combinational circuit design, apart from the addition of these extra steps here. So we still get a specification, we still have to do a formulation. In this case we do state diagrams or a state table. We need to do a state assignment, which is something new, which is to assign unique binary codes to the states themselves. Then we have flip-flop input equation determination, which is a long way of writing what are the inputs to the flip-flops, remembering that we can use the flip-flops as storage elements to store the states. Then we do the output equation determination, where we derive the output equations from the entries in the table. And then we go back to our normal steps, which is to optimize these equations to map the technology depending upon what the specifications are. That might be we need to use NAND gates, or we may need to use NOR gates, or we have certain flip-flops available in order to implement our optimized equations. And finally, we verify that the final design that we've created is correct according to the specifications. In terms of the specifications, there are a few other details compared to the combinational logic circuit design, which I haven't talked about before, and they are the ones with stars. So previously we mentioned that we would get a written description or perhaps a mathematical description. However, it's also possible that the specification gives you a hardware description language or tabular, equation, or diagrammatic descriptions. The fact that these have stars against them is just to let you know that it's a much more rigorous binary level specification, and it can sometimes be possible to just simply skip the formulation step if you have this level of detail. In the formulation step, different to before, we now need to find a state diagram, remembering that the state is some sort of abstraction of the past applied inputs. We can give the states labels or names or binary values, and this is really just a formal way of saying that the interpretation of past inputs is tied to the synchronous operation of the circuit. There are asynchronous input values such as a reset. However, the normal input values are measured only during the setup hold time interval for an edge-triggered flip-flop. And some examples of that, which will make it a bit clearer. Think about a state A as representing the fact that we've had a certain input in order to get there. So let's say we were in state Z. In order to get to state A, then it implies that there's been some sort of input. And in this case, the input is 1. And then state B represents the fact that we had a 0 as the most recent input, and then a 1 as the input before that. So it's this idea of chaining together past inputs in order to move through states, in order to get to the current state that you're in, or a particular state. When we're specifying the circuits, we use these states to remember the properties of the past input sequences that are essential to predicting future output values. It's a formal way of writing the fact that based upon our previous example where we had Z going to A, going to B, then we need to keep track of which state we're in, which also inherently tells us what this sequence of inputs was. In this case, we had 1 and then 0 in order to get to the state B. These states inside the state diagram allow us to keep track of where we're up to and where we can potentially move in the future. Perhaps that's to a state C, or maybe it's also back to a state Z. So if we're doing a sequence recognizer, where we're trying to recognize a sequence of input values that have happened, maybe in this case a 1, a 0, and then a 0, before we give some sort of output. So these state diagrams allow us to find patterns or to recognize sequences of input symbols. And so we're going to be developing a procedure that's specific to the sequence recognizer, because that's the sort of problem that this subject would like you to understand. So you'll need to be able to convert this problem statement into a state diagram, and the state diagram will be the way of recognizing the sequence. After we have the state diagram, we're going to be converting this into a state table, and from the state table we can then pull out our equations, do our optimization, and design our circuit based upon that. And if this very wordy slide is not immediately obvious, the examples that will follow, particularly in the next part, assuming that you work along with the video as it's happening, will certainly clear up your understanding of some of these abstract terms. Another issue we're going to look at is state assignment. Up until now, we've always just assumed that the states are given to us, whether that be A, B, or whether it be binary values. However, since the states are going to be stored inside the flip-flops themselves, inside these memory elements, then it's important that we know how many bits that we need to store so that we can have unique codes. Given the M states, then we need each of those M states to have a single unique binary code. Remembering from lecture 1, where we talked about how many bits were required, we need to make sure that we provide enough bits, N, and enough storage elements so that we can store each of the M states. Since we need for M to be less than or equal to 2 to the N, for example, if we need 4 states, then we need at least 2 bits, so that's less than or equal to 2 to the 2. If we needed M to be 6 states, then we need at least 3 bits, 2 to the 3, and then there will be 2 to the n minus m unused states. In the first case, we had 2 to the 2 minus 4 gives 0, so there's 0 unused states. In the second case, we have 2 to the 3 minus 6. In this second case here, 2 to the 3 minus 6 is equal to 2, so we have 2 unused states. And ideally, we want to minimize this number of unused states whilst minimizing the number of bits required, therefore the number of storage elements, whilst still making allowances for the correct number of states in our state diagram and state table. So this is the sequence recognizer procedure, and we're going to go through an example in part 2 of a sequence recognizer. In order to develop the sequence recognizer state diagram, we begin with an initial state in which none of the initial portion of the sequence has been recognized or has occurred, and that's typically what we would call a reset state. So the user has pushed reset. If it makes it easier to imagine, think about pushing in some sort of password into a little embedded system, and your password perhaps is your student number. In order to recognize that sequence, we need to start from a known initial state. That can be from reset, the place where none of your student number has been recognized yet. You haven't entered any of the values yet. Then once the first symbol has occurred, maybe the first number of your student number is a 1. Once the 1 has occurred, then we need another state, which tells us that we've moved from the initial state to this particular state because the first symbol has occurred. Then we need states for each successive symbol. So maybe your student number is 1, 0, and more numbers. Then for each of these, we need to have a new state. But it is possible sometimes that we have repetitions which allow some of the states to transition to each other, but we'll get into that a bit later. And then we need a final state where we've recognized that there's an input sequence that's happened, and then we usually have some sort of output confirm that that sequence of symbols has occurred. Then in our state diagram, we need to add the state transition arcs, which are simply those lines with arrows on them that connect the states together, telling us that we can go from state 0 to state 1 given an input of x equaling 1 for the first number of the student number here. And remembering also that if the first number is not the sequence that we wanted, we have to specify another state transition arc for what happens there, because obviously if x is equal to 0, then we don't want to transition to 1. We perhaps want to stay at state 0. And this last step, which adds all the arcs on non-sequence inputs, is required because the circuit really needs to be able to recognize the input sequence that we're looking for, regardless of where it occurs within the overall sequence applied since the reset. Okay, so that's the end of this part. In the next part, we're going to be doing a sequence recognizer example, which is a much more comprehensive and pictorial representation of the sequence recognition required for this sequential circuit design. So I'll see you then.